Hello everybody, welcome to my talk about BigTrace plugin. I will start with the motivation behind its development. In our lab, we study microtubules. These are intracellular polymers with many important functions. For example, during division they form spindles, shown here, that spatially separate DNA between daughter cells. In non-dividing cells, they form complicated polymer networks which shape depends on the cell type. In this example, it is a microtubule skeleton of a white blood cell. And this movie shows microtubule organization in a muscle cell of a heart. As you can see, it is completely different network with different compartments colored in red and green here. We are interested in extracting geometrical and topological properties of these microtubule networks and study how they change in normal and pathological conditions. We work with volumetric datasets that are relatively large. Not insanely large, but big enough to saturate an average computer memory. And what we want to extract out of them are segmented curves. So basically transforming volumetric fluorescence data to a table or a set of curves where each curve would be represented as an ordered list of 3D coordinates. This will allow us to quickly and efficiently analyze properties of these curves like length, smoothness, persistence, distribution of ends, and so on. So the task was clear, and together with future users we assembled a list of desired features that this hypothetical software should have. And before jumping to the coding, we decided to ask one very important question. Do we really need to write this plugin, or maybe we can just use something else that already exists? And in principle, extraction of curvilinear structures is an old and very well developed topic for analysis of neurons and blood vessels. Basically, they both are intensity curves from image analysis point of view. And there is a substantial amount of great software for this problem, some of which is shown here, and of course this list is far from being full. Well, the short answer to our question is probably not. In principle, a combination of existing solutions can solve all our problems. But on the other hand, development of your own software really helps to understand problem specifics. So, considering the educational context, we decided that, well, maybe we will give it a shot. For plugin implementation, we chose what I call a Java ecosystem, mostly because A, there are a lot of image analysis libraries available, and B, well, because I have much more experience coding in Java. Most widespread Java plugin for large 3D microscopy data is probably, in my opinion, Big Data Viewer. It is really great, but it is slice-based, and we wanted to have some real 3D rendering, so we turned to its cousin, Big Volume Viewer. And this plugin has its clear advantages, so it's really possible to render large data sets on 3D. On the other hand, comparing to the Big Data Viewer, it has much less additional tools developed around it, and it's more like proof of concept, which was mentioned by its author Tobias Pirch. So it's like a bare data viewer. So we decided to implement some additional features in the user interface. We added a box around the volume and origin of coordinates for the visual guidance. Also, we added scales to account for anisotropic pixel dimensions. Since our polymer network is so dense, we wanted to have a possibility to crop the volume to focus on some specific parts of the sample without obstruction from the rest. This feature turned out to be pretty helpful, and it makes manual analysis much easier. On top of that, we added some ROI primitives, like a point selection tool that allows you to mark some locations in 3D, and polyline tracing tool, which is basically just a set of points that are connected by straight lines. All of them are governed by a ROI manager shown here on the right, which is heavily inspired by a classic ImageJ ROI manager and was honestly made to look a bit like it. So you can change ROI appearance, color, delete it, and etc. etc. They're pretty basic and simple and don't look fancy, but they do the job. And finally, we were able to implement semi-automated curve tracing tool. In this case, user sequentially selects points in the curve, and software automatically finds the best path between them along the curve. This functionality is kind of similar to many other curve tracing plugins, and it is easier to look at it in 3D to resolve intersection. We chose to implement it as this small moving trace box, well, that you can change in size in principle, which follows this active tracing point. And it turned out to be much easier to know what you're doing, to see where you are in the small volume comparing to showing, like the whole sample at once. Also, it's much less computationally heavy, and it can be done fast and basically on the fly, even on the average laptop. The other feature that we implemented is the possibility to unite different ROIs and ROI groups. Basically, each ROI must belong to some group. And here different groups marked with different colors. So you can group different biological staining, and you can change appearance of all ROIs and groups in the same way you can change like individual ROIs. Also, you can save and load these group settings. And of course, in the viewer, you can choose which groups can be displayed and visible in the main window. Another feature that we added is handy for large datasets. If you click on some point, plugin can zoom in on this area, so you can inspect local neighborhood. It is useful for 3D views of large datasets. If you rotate and zoom on whole volume, it can be confusing and take a long time. And this is like a classic 2D zoom model as well in 3D. So this is the link to the GitHub. You can download and try plugin yourself. I must warn you that this is a first public release, and this project is really at the initial stage. It's very basic and probably buggy, and there are still a lot of additional features that we'd like to implement, but this is a start. And at this point, after functionality presentation, I'd like to mention some details on the implementation. So the main problem for this semi-manual curve tracing parts was how to find the path between two dots clicked marked by user, shown in red here, that it will follow this line along the bright curve. And in this case, people usually use some variation of famous Dijkstra algorithm to find the minimal cost route, which is illustrated on the right. As you can see, this algorithm is like a greedy flood fill, which means it has to visit all pixels before it finds the shortest route. It means it is pretty expensive computationally, and for 2D data it's forgiven, but for 3D data amount of voxels is huge. So if you can reduce the search area by volume somehow, you can speed it up considerably. The cost or weight of each pixel is usually computed as a single value from a Hessian matrix. So what is this Hessian matrix? Each 2D image in principle can be considered as a 2D function, and the Hessian matrix is a matrix of second derivative of this function, and it can be calculated for each pixel. In addition, you can derive 4 important outputs out of it: 2 scalars, so-called eigenvalues, and 2 eigenvectors. These eigenvalues specify approximation of intensity shape in the local neighborhood of the pixel. So just looking at their signs and values, you can say if pixel belongs to the point, or it's a line, or it's a saddle. So by carefully analyzing both eigenvalues instead of single general tubiness characteristic, it's possible to remove pixels from the area where the greedy Dijkstra algorithm will be filling. In this case, what I'm showing in the green is the pixel where you limit where the search can happen, and this way you can limit the search. And the red points joined here, so the algorithm doesn't have to go through all the pixels of the volume. It can just move through this green area, which makes it much faster. And this is especially important in 3D, since the things really blow up in there. This approach works really well, but it has its downsides. For example, if the curve has gaps, and so selected points are located in a non-connected area of this allowed search area. For this, we developed an algorithm of jump points calculation. It's also based on the Hessian metric eigenvalues analysis. I will not go into details on it now, but one can select these so-called jumping points, which are located mostly at the tips and boundaries of the curves. And then one can run 2 Dijkstra algorithms for 2 areas around 2 points that should be fast, since these areas are pretty small, and then find jumping points that were included, which marked here in pink, and quickly find two closest jumping points among this set. Since these jumping points are the tips, one can simply connect them by a straight line. And this combination works much faster than still visiting all voxels of the dataset and using the classic Dijkstra algorithm. So for Hessian analysis explanations, I used, of course, here an example of 2D data, but in 3D situation is a bit more complicated, of course, but again, you can correspond eigenvalues and their values to a set of simple basic shapes, which is shown in this illustration. And here is a quick jump points illustration on 3D dataset. As you can see, they like to sit at the tips and boundaries of the curves, and so the tracing points with these jump points, you can be considerably sped up comparing to the classic algorithms. At this point, I'd like to finish and thank my collaborators for help, data and discussion, and thank you for your attention.